Okay, so I'm going to do 3 things in this video. Eventually what I'm going to do is I'm going to find the gradient of this surface at the point P, and I just chose the point P to be root 2, 4. Okay, this is the equation for the surface. And then eventually I'm going to find a tangent plane approximation to this surface at the point P, and I'm going to plot it using a plotter that I found online that I used in a previous video. But before I do that, I said in the last video that I was going to sort of prove that gradient vectors were perpendicular to level curves. So I'm going to do that now really quickly. Okay, so here we have some surface where I said that z equals some function of x and y. Okay, so you can think of that. You can think of this surface like that, like it's or z is a function of 2 variables. So we have like this 3-dimensional surface, or you can think of it like this, where you just subtract z from both sides. Okay, so that equals 0. And then you can say that this left side of this equation here equals some other function of x, y, and z. Okay, so it's basically what you're saying here when you write this like this is you're saying that you have this higher dimensional function. Okay, so this is like some 4-dimensional function here, and when you write it like this, you're saying that this surface that I drew here is a level surface. A level surface, not a level curve, a level surface of this function when this function equals 0. Okay? So, see here I actually wrote this wrong. What I should have wrote instead, I'll explain this in a sec though, is that I'm trying to find, or what I'm going to show you is that when I find the gradient vector of this surface evaluated at point P, I'm going to show you that it is indeed perpendicular to this level surface. Okay? So the way that I do that is I say, okay, so the point P is some point on this surface, and there's a position vector pointing from the origin to point P. Okay, so I'm saying that r of t equals a function of x, or equals x, where x is a function of t, y, where y is a function of t, and z, where z equals a function of t. Okay, so it's just a regular parametric equation of this surface here, like we've done before. Okay, where there's just one parameter. You know, maybe there's a curve or something, like a curve that goes along this surface, goes past point T, and maybe this position vector points to a point on that curve that crosses point P on this surface. Okay, so if this position vector points to a point on this surface where x is a function of t, y is a function of t, and z is a function of t, then you can also write f, where f is a function of x, where x is a function of t, y, where y is a function of t, and z, where z is a function of t. Okay, so then little f will be function of x, which is a function of t, and a function of y, which is a function of t, and then z is z, but z is a function of t as well. Okay, so just to clean this up a little bit, I'm just gonna make some space here. Okay, so I just moved this up here just to clean it up a little bit. Okay, so I can take the derivative of both sides of this equation here with respect to t. So, but in order to do that, I'll have to use the chain rule here, because f is a function of x, but x is a function of t, and f is a function of y, and y is a function of t. So if I want to take the partial derivative of f with respect to t, what you do is, you apply the chain rule at each step here. So I take the partial derivative of f with respect to x, and I multiply that by dx dt. I take the partial derivative of f with respect to y and multiply that by dy dt, and then I take the partial derivative of f with respect to z and I multiply that by dz dt. And then on the right hand side I still have 0. The derivative of 0 is just 0. Okay, so like just, I don't know, since I haven't gone over the chain rule, I guess I'll just quickly say that some people like to remember it like this. Okay, so what you do is, like, whenever you want to take the derivative of a function with respect to like another variable that's you know, sort of like indirect here like this, what you do is you have to take the partial derivatives of your function with respect to all of the variables that are functions of the other variable, and then you multiply it by this derivative here, where you take the derivative of like one of these variables with respect to the final variable that you're trying to take the derivative respect to of the original function. So you can see here, if I wanted to find df dt, I take the derivative of f with respect to x, I go down this path, take the derivative of f with respect to x, and then I multiply that by dx dt, then I take the derivative of f with respect to y, multiply that by dy dt, then I take the derivative of f with respect to z and multiply that by dz dt. Add them all together like this. Okay, so we know that the gradient of f is going to be a vector of f sub x, f sub y, f sub z. Okay? So we can see these terms right here. Okay? We also know from a previous video that I did with you, where if you want to find a tangent vector to some curve or some surface where you have like a position function or a position vector like this, then you can find, I think I wrote it like this, the tangent vector is going to be simply, you know, if you want the unit tangent vector, then you multiply this by the length of this vector that you end up with here. So what would that be? This would be a vector whose components are dx dt, dy dt, dz dt. And you can see that those guys are showing up here. Okay, so what this equation over here is actually telling us is that if you take the gradient of a function and you dot it with a tangent vector, then this is going to equal 0. Okay, so what's the tangent vector? So the tangent vector is a vector that is tangent to the surface at the point P. Okay? So if the dot product between this tangent vector and this gradient vector is 0, then that can only mean one thing, that these two vectors are perpendicular to each other, which means that, therefore, the gradient of a function is normal to its level curves or surfaces. So that's sort of my little proof here. Okay, so in this example, we want to find the gradient of z at the point P. Okay, so what we're going to end up finding is a vector. So this is our surface. We're going to find a vector that's perpendicular to one of the level curves at the point P. Okay, so I'll just say that we're going to find the gradient of z at the point P, where P is root 2, 4. Okay, so First, let's evaluate the gradient of z. Okay, so it's going to be a vector with the partial derivatives. So if we want to find the gradient of z at the point P, then it's going to be 2 root 2, 2 root 2. Now, let me show you that this is actually perpendicular to this level curve at that point. Okay, so the way that I'm going to show that is I'm going to say when z equals 4, we have the level curve x squared plus y squared equals 4. Okay, so in the xy plane, that's just going to be a circle of radius 2. So where would the point root 2, root 2, 4 be on this level curve? Well, it's a point right here. So that would be the point P xy, where it's the projection of P down onto the xy plane. If I wanted to know a position vector that pointed to that point, what would it be? Well, it would be root 2, root 2, right? It would just be a vector that points to that point there. Okay, so how am I going to show you that the gradient vector is perpendicular to our level curve at the point P sub xy? Well, we can do what I said previously, where I find a tangent vector at the point P sub xy, and then I compute the dot product and show you that the dot product is 0. But I'm not going to do that because I don't have this position vector. I don't have this surface parameterized. I don't have R parameterized or anything. So instead of doing that, what I'm going to do is I know that if I take the gradient of z at the point P, and I take its cross product with this position vector here, I know that I purposely picked this example where in this case, all of my gradient vectors are going to be pointing in the same direction as any position vector that points to any point on the level curves. So I know that if I take the cross product between two vectors that are parallel like this, then the cross product is going to equal 0. So that's what I'm going to do. I'm going to take the cross product. Okay, so if I want to take the cross product between the gradient of f at P, that's this guy up here, and if I want to take the cross product with this guy here, then I have, okay, so when I compute this, where am I? So when I compute this cross product, when I find the component of the cross product that points in the I hat direction, you can see I ignore that column. In this row, I have 2 root 2 times 0, take away root 2 times 0, so it's just going to be 0 in the I hat. When I compute the component of the cross product that's in the negative j hat direction, I ignore the middle column here, and in the top row, I find the determinant of the subdeterminant here. So I have 2 root 2 times 0 again, and then root 2 times 0, which is 0 again. I just ignore the negative sign there because it doesn't matter, because I have 0. And then when I compute the component of this guy in the k hat direction, what do I have? I have 2 root 2 times root 2, which is going to be 4. And then I have root 2, or takeaway, root 2 times 2 root 2, again, which is going to be 4, and that's in the k hat direction. 4 take away 4 is 0. I just get a 0 vector here, right? So maybe I should have wrote that. So that tells us that R is a position vector that points from the origin to the point P sub xy, which is the projection of P down onto the xy plane. And then when I find the gradient at P, it gives me a gradient in the x. It gives me a vector in the xy plane, and then when I take their cross product, I get a 0 vector, which only means that r and the gradient of f are parallel to each other. So hopefully that wasn't too confusing. I know that this video is already starting to get long. What if I wanted to find a plane that is tangent to this surface at the point P? Well, in order to do that, I need, well, one of the ways I like to find tangent planes, if you might remember from like linear algebra or something like that, when you have the equation of a plane, like a x plus b y plus c z equals some number, well, a, b, and c are the components of a vector that's perpendicular to the surface of this plane. Okay? So that means that if I can find a vector that's perpendicular to this surface at the point P, and I know where the point P is, it's given to me here, then maybe I can sort of plug all of that information into an equation like this and end up with the equation of a tangent plane. Okay, so if I want to find a vector that's perpendicular to this surface, how am I going to do that? Because I just found the gradient of z, and it was a vector that was perpendicular to one of these level curves in the xy plane. That's not what I want. So what I want to do is similar to like what I said before about how I think of this surface as if it's, I rewrite it sort of like this, where I think of it as like a level surface to some higher order function that's a function of x, y, and z, like this. Okay? So I didn't do anything. Like I introduced this higher order function, and I'm looking at a level surface of that function in three-dimensional space where that function equals 0. Okay, so you can think of it like this is some four-dimensional surface, and when it equals 0, this surface intersects three-dimensional space like this curve here. Okay, so if I can find the gradient of f, at the point P, then I will have a vector that's perpendicular to this surface. Like we said, when you find the gradient to a function, its gradient is perpendicular to the level curves, right? Well, here, when I find the gradient of f, the gradient is going to be perpendicular to its level surfaces, and this is the level surface. Okay, so when I do that, I get a vector like this, and when I evaluate that at the point P, I get something similar to what I had before. I have this three-dimensional vector here with this -1z component. Okay, so if we believe that what we learned in linear algebra, that the coefficients of the x, y, and z terms here are perpendicular to this plane, this just this generic plane here, then we can say that, alright, well, then we can say that we have a vector that's perpendicular to a surface at P. Okay, so maybe we have something like this. X plus, okay, so equals some number d. Okay, so what would this number d be here? Okay, so like I want to be clear here. These coefficients, when we learned way back in linear algebra, we learned that like a normal vector to this plane is a vector whose components are these coefficients here. Okay, so that's what I'm saying here, that these coefficients are the components of a normal vector, and because of the definition of a gradient vector, we're saying that since the gradient vector is perpendicular to a surface, this particular surface at this particular point P, then these coefficients here are going to be vectors are going to be the components of a vector that is perpendicular to the surface. Okay, so we're almost there. All we need to do now is find D. So if this point is on this surface at P, and this is the equation of a tangent plane at P, then they share that same point P. So that means that these points, this point P, has to also be on this surface here, which means that we can plug in the values for x, y, and z to obtain D. So when we do that, we have, so D is going to equal this. So 2 root 2 times root 2, that's 4. Okay, so 4 minus 4 is going to equal 0, and that equals 4. So that means that D equals 4. Okay, so now what can we do? Well, I can divide everything through by 2 here to kind of make things a little bit simpler. This equation here is going to be the equation of a tangent plane that's tangent to this surface at the point P. So to show you, okay, so here I am in this little graphing applet that I got off the internet, and I already input the equation of our paraboloid here, z equals x squared plus y squared, so I plotted that. Now I'm just going to put in our plane here. I have to solve this plane in terms of z, okay, so maybe I shouldn't have divided through by 2. So when I input this, 2 times square root of 2 times x. Okay, so there you go. I'm just going to changing my some of my domain and range and all that kind of stuff, and I added in the point root 2, 4. Okay, so you can see here I put in a plane for where z equals 4. So you can see that it slices our graph at that point there, and I added the point root 2, 4. Make it a certain size and color, and it corresponds to that point there. So you can see that the equation of the plane that I inputted is indeed tangent to this surface at the point root 2, 4. Okay, so thank you very much.